Okay, so now we're going to talk about the product quotient rules, some extra trig identities, and higher order derivatives. So the first thing we're going to look at is the product rule. So let's say that we had a function, f of x, that equaled the product of two other functions. So we'll call them g of x and h of x. Well, the rule says this, okay? So we pick one function to be our first, and we pick another function to be our second. Okay, so when you go through and you try to find the derivative of f, the derivative of f is a combination between g and h and the derivatives of g and h. So this is going to be, I always think of it this way, that you have your first function, okay, and you multiply that by the derivative of your second. You then always add your second function, which is we called h of x, times the derivative of our first function, which is g prime of x. Okay, so it's a combination of each of the functions from the product by the derivative of the other function, and we have to add them together. Now, the next rule, the quotient rule, it derives from the product rule, and it's a little more complex, and it's much more specific as to how you have to do it. So there's a bunch of different mnemonics that people use to memorize it, but I'll show you the one that I found to be the best. So if we know that f of x equals a function g of x divided by a function h of x, the way that this derivative is going to be, and we'll designate this one as green and this one as blue. Or actually, okay, so that's pretty consistent. Good. Okay, so what we have to do here is write it as follows. The derivative of f of x is going to be h of x times the derivative of the g of x, always minus, okay, it's always a minus this time, and that's going to be, and then we're going to do the opposite, so it's sort of like the product rule, where this is going to now be g of x times the derivative of h of x, all over h of x squared. Now, there's a different way to remember this, because that seems, lots of x's, g's, and h's. How do I memorize all of this? Well, somebody at one point said, why don't we call these two functions, we'll call the one on top, we'll call this the high function. And we'll call the function on the bottom the ho function. Okay, so you end up with this funny little jingle. So, first off, we're going to have our high function, which our high function is just g of x. And our ho function, or excuse me, we then need to think about what our d high function is. So this is the derivative of the high function, which is just going to be the derivative of g of x. We then have our ho function. So our ho function, that's going to be h of x, and our d ho function is just h prime of x, and this is our little blue guy, so h prime of x. So we think of this in a few different ways, but it comes with this funny little jingle, where now, when we direct replace all of these things, it's actually kind of funny. So we're going to get ho, d high, less high, d ho, over ho-ho. So it's the same thing. It's just easier to remember, hey, our high function is the top one. Our ho function is the bottom one. Well, if I remember ho d high less high d ho over ho ho, then I can remember the order to put them in. You just have to decide which, what the derivatives are of each individual function and then put them together. Then the rest after that is just algebra. Next thing that we need to look at are, are more trig identities. And so I'm going to give you our previous ones. We knew that the derivative of sine was cosine. And we said that the derivative of cosine is negative sine. Well, there's a pattern that hopefully you'll find that makes things maybe a little bit easier for you to figure out. Well, the next set would be, let's say, what's the derivative of tangent? Well, you'll notice that if it doesn't have a co in front of it, it'll always be a positive. So tangent links with secant squared here. So the derivative of tangent is a positive secant squared, where the derivative of cotangent, well, this starts with a co. This is negative cosecant squared. So again, it's a negative answer because you're taking the derivative of a co-function. And this one links with cosecant squared as opposed to secant squared. Now, as we go down, the last couple functions we have are secant of x. Now this one, again, we've linked secant and tangent so far. So the derivative of secant, this one is a positive secant x cotan, or excuse, tan x. Now, if you're clever, you can probably figure out already what the derivative of cosecant of x is going to be. Again, because it starts with a co, the derivative is going to be negative, and instead of secant and tangent, you're going to have cosecant, cosecant x, cotan x. So these are kind of strange, but there's a pattern to it. And if you can understand the pattern, then you can kind of understand how the rest of this works. But these are going to be important ones to know because you'll have to take the derivatives of these at different times. And now, lastly, we are dealing with higher order derivatives. And the way they decide to describe this is in terms of something moving. Well, if we have something moving, so let's say there's me. I'm in my room. I just graded a bunch of really bad tests, and I want to jump onto First Street. Right? Well, there's a bunch of different ways that we can describe, what I'm doing here. We can describe, with math, where I am on my path to First Street. As I get closer. We normally call this the position function. And so our position function is normally written like this. S of t. Why they use S, I don't know, but they do. So this is our position function. It tells me that at a particular time, I'm at a particular position S. Well, if I were to take the derivative of my position function, okay, so as my position changes over time, so position over time, well, we generally call that velocity, which we signal as d of t. Okay, so if I took the derivative of my position function, I'm taking the derivative with respect to my variable time. Instead of x like we have been used to, my variable now is time, because I'm talking about physics problems and movement. So position over time gives me velocity, which is v of t. But that's the same thing as the derivative of position. Now, here's something interesting. Okay, now I can actually look at the second derivative, another derivative. So a derivative of a derivative, and that tells me something else. This is the same thing as position over time, right? Because I'm respecting it with time again. Or that's the same as velocity over time, which if you remember your physics, we call acceleration, which we call a of t. So there's another function that we can find, the acceleration function, and that's just the derivative of velocity, or it's the second derivative of position. So they all link in this particular way. So we could say, the second derivative of t is the first derivative, or the second derivative of position is the first derivative of velocity, which is acceleration. So we can take multiple derivatives, as many as we want. Now they don't all mean as much as these mean together, but you can keep going forever and ever taking derivatives. That's an important thing. We can always take a derivative, we can always keep going. Now eventually a lot of functions just zero out, but this is a really important concept that links all of these things together. That position, velocity, and acceleration are all linked together by derivatives.